Hello everyone, and welcome to the North Carolina Smart Grid webinar series. We're pleased that you decided to take time out of your schedule to join us today. My name is Alex Glenn, and I work with Advanced Energy as a training consultant and instructional designer. I've worked in the energy industry for 15 years, and I'm happy to be your host and facilitator for today's webinar. As an independent nonprofit that works with most of North Carolina's electric utilities, Advanced Energy's mission is to help our state's electric utility customers get the most value out of the money that they spend for energy. To help our state's residents make well-informed energy decisions, we want to share information about new technologies and services when we believe that they can offer value. And we also want to share any concerns that may present risk. This webinar series is being developed using the North Carolina Public Benefits Funds administered by Advanced Energy and Duke Energy, along with generous technical support from North Carolina's electric membership cooperatives, Duke Energy and Dominion NC Power. North Carolina's electric utilities are modernizing their power generation and distribution systems. This transformation of our electric grid offers improved performance and growth opportunities for citizens, communities, and businesses. We're pleased to bring you information about smart grid technologies and systems that are being deployed in North Carolina and how you might be able to benefit from them. Today, we bring you the fourth webinar in our series, Microgrids and Grid Resiliency. In this webinar, we will provide an overview of microgrid technologies and examples of how they're being used and implemented here in North Carolina. We would like to hear from you during this webinar. Please feel free to post your questions or comments in the Q&A box on the upper right side of your screen. We will address your comments and questions as we can during the question and answer period at the end of our presentation. Also, as a reminder, please feel free to join us for the last webinar in our series on October 24th, where we'll be covering new information about self-optimizing systems. I would also like to mention our website, where all of our smart grid resources are available to you. We have posted case studies, educational videos, upcoming events, and links to all of the smart grid resources. So please make sure to visit ncsmartgrid.org to access this wealth of information. And also note that a recorded version of today's webinar will be made available to you. We will send a follow-up email where you can access the webinar recording as well as the additional links to the smart grid resources. So please keep a lookout for that email at the end of the webinar. In today's webinar, we will recap a couple of key points from our previous smart grid webinars, and we'll dig deeper into the top of microgrids and grid resiliency in North Carolina. We're pleased to have two speakers, C.C. Maurer and Tom Fenimore, who will provide an overview of microgrids and examples of how microgrids are being implemented in North Carolina. At the end of today's webinar, we'll also be sharing a video from Duke Energy about a microgrid system in operation for a critical services facility at their McAlpine location. We hope that you'll stay with us until the end of the webinar to watch the video. C.C. Maurer is a professional energy engineer with Advanced Energy, and she has worked on our building science and engineering teams. Her current work focuses on managing the technical staff and smart grid education. C.C. will provide an overview of microgrid technology, policies and economic factors, and the challenges and benefits of microgrids in North Carolina. Tom Fenimore will come up next. He's a professional engineer with Duke Energy and is the Technology Development Manager in the Emerging Technology Office. Tom has been with Duke for over 20 years in a variety of roles. He is currently leading projects in the following areas: microgrids, energy storage and distributed energy resources, distributed generation control development, and DC bus integration. Tom will provide us examples of microgrid systems and how they enhance Duke Energy's customer services. At this point, I'm going to turn it over to our first speaker, C.C. Maurer, who will deliver her section of our presentation. Cece?
Thanks, Alex, and thanks to everyone for joining us today. I'm going to start with an introduction to microgrids, cover technology basics, and then talk about some of the policies, economic factors, challenges, and benefits. We will start by reviewing a few key points from the previous Smart Grid Basics webinar. This slide shows a way to visually define Smart Grid. You can picture it as the integration of modern technology on the electrical infrastructure with advanced communications and controls overlaid as an intelligence infrastructure. The intelligence allows more information to be collected and analyzed from the generation plants to the customer site. The traditional grid has large central generators sending power in one direction to customers, often many miles away. A typical conventional generator can produce more than 1,000 megawatts of power. The smart grid will be able to integrate distributed energy resources such as solar and wind and other renewable facilities. These resources are much smaller and are located closer to the customers who are using the power, on the scale of 5 kilowatts to 50 megawatts. The microgrid applications that we are talking about today are generally on that scale. The US DOE definition of a microgrid is a group of interconnected loads and distributed energy resources within clearly defined electrical boundaries that acts as a single controllable entity with respect to the grid. Microgrids are independent power systems that can take over for the electric grid during a power outage. Let's take a closer look at the key features that define a microgrid at a high level. Interconnected loads could be a campus, a single facility, or a neighborhood. Some microgrids may incorporate load management or control within homes or facilities. Distributed energy generation resources could be solar, wind, diesel, natural gas, or biofuels. An energy storage system will be required if solar and wind resources are used. Solar and wind are intermittent, and the storage system will make power available all the time. The energy storage system may be used for backup power or demand response, or both. With the integration of generation and storage, microgrids have the potential to provide what is called ancillary services for the utility, such as load management, voltage, and frequency regulation. Islanding capability is a key feature of a microgrid and is defined as the ability to disconnect from the grid and island for short periods of time, referred to as island mode. This transition from the grid to an island mode can be seamless for a modern microgrid, with no downtime of critical loads such as manufacturing lines, IT equipment, or heating and cooling equipment. This switch from the grid to island mode could be weather-related or due to some grid issue, but it could also be an intentional disconnect from the customer or the utility for load shedding. This ability to island is why a microgrid is called a single controllable entity. And the loads, generation, grid connection, and storage are all connected through an intelligent and automated control system that also communicates to the electric utility. Weather forecast and energy pricing data can also be used to manage microgrid operation and optimize their performance. Microgrids can come in many sizes. As stated by the Microgrid Institute, they are defined by their function, not their size. Some microgrids can be small off-grid applications at remote sites that power a single load, while others could be a whole campus or neighborhood. Weather-related events are the major cause of power outages in the Carolinas, with the largest being hurricanes, then winter storms, and then summer thunderstorms. Hurricanes and winter storm outage times, on average, have been 30 to 43 hours for those affected. Other outage events are much shorter, from only a few seconds to a couple hours. Both resiliency and reliability are terms used in relation to power outages. We want to make sure to define these terms and give a broad perspective on their importance. On a basic level, resiliency means being able to maintain services in spite of an outage. A more detailed definition is the ability to prepare for changing conditions and withstand and recover rapidly from deliberate attacks, accidents, or naturally occurring events. Resiliency means planning for infrequent but highly critical events. Reliability is defined by the amount of time the grid is available and is more about planning for the common frequent events that can occur, such as voltage and frequency regulation and maintenance of distribution lines. We are striving for both resiliency and reliability with grid modernization and microgrid integration. There are some common current applications for microgrids. Military bases often have requirements for backup power, and the alternative is standalone generators. Island and remote areas where traditional power is usually expensive. Municipal and county facilities such as emergency response or water and wastewater treatment. Many university campuses already have centralized electrical and heating and cooling infrastructure. And then certain industries such as hospitals and data centers which have critical power and emergency generation needs. In general, any places that have aged infrastructure that already require investment and replacement are candidates for microgrids. Let's take a look at some of the basic components of microgrids. The generation or source of electricity can be a diesel or gas generator. Animal waste or landfill gas could also be used as a renewable fuel to run a generator. Diesel and gas generators have commonly been used for backup power systems. However, these systems take enough time to start up that traditionally the transition to backup power is not seamless and the electricity may briefly go out. Also, generators do require maintenance and can be noisy to operate. They have energy available at any time as long as there's enough fuel storage for diesel or a connection to the gas pipeline. On the other hand, solar and wind are intermittent renewable resources and do require a separate energy storage system. Solar is the primary renewable resource being utilized in microgrids locally. Grid interconnection requires a system of power conversion equipment, switches, protection devices, and meters. Peripheral equipment for power conversion, such as inverters and transformers, shown here, allow the power produced by the generation to be connected to the grid. One type of switch used in distribution systems is called a recloser. If there is an event with an abnormal electric current called a fault, the recloser will disconnect. When the event is over, reclosers have controls that will automatically reconnect when safe. A specific application for microgrids is called an islanding switch, which is used to disconnect the microgrid from the main grid. The islanding switch may be triggered by a weather-related event or other grid issue, but it also could be an intentional disconnect from the customer or utility for load shedding. Another protection device shown here is the disconnect switch for the battery system. All parts of the microgrid may need to be maintained in isolation from one another, and these disconnects are an important safety feature. Lastly, meters are important to collect information about the overall power output or input at various points in the system. These are used to measure generation, auxiliary power, and customer load. Meters also provide feedback on voltage and power quality. All of the above parts contribute to the overall cost of the microgrid. Another essential component of a microgrid is energy storage. Many microgrids rely on battery technology, and like with other storage systems, the utility is interested in using the batteries for both backup power needs and for managing peak loads. Batteries are electrochemical storage, and there are numerous chemistries that can be used. We do not have time today to go over battery technologies in detail. However, if you're interested in this topic, note that we are considering it for a future webinar. Please let us know when you take the survey at the end of the webinar whether you are interested in learning more about battery technology and applications. Battery systems will have both a power rating in kilowatts or megawatts and an energy rating in kilowatt hours or megawatt hours. Batteries will have different cycling capabilities and depth of discharge. It's important to consider all of these factors in an energy storage system design to compare the technologies. Batteries also have an optimal temperature at which they operate. This means that many batteries need a dedicated conditioning system. In field applications, this has proven to be suboptimally designed for battery performance. The conditioning contributes to the overall auxiliary power requirements for the battery energy storage system and the microgrid in general. All of the equipment described must communicate continuously. The control system for a microgrid involves monitoring real-time data on the grid with the generation system, the load, and the storage system. With all of these different inputs and control strategies, each microgrid controller is generally customized for their application. This is a screenshot of the control system for Duke's McAlpine microgrid. We will look at a few key parts of the microgrid that were described on this monitoring system. The top portion of the screen represents the grid, and the bottom portion represents the microgrid. Here you can see the power produced from the solar. You can see the voltage on both sides of the transformer. On the right side, the output of the generation and battery system is displayed. And then on the left side, the grid voltage is shown. In this case, the microgrid is connected to the grid. You can see the voltage of the grid and the power imported from the grid to the microgrid. Power information is also collected on both the customer load and the auxiliary power required to keep the microgrid running. The customer load in this case is the fire station. The auxiliary power is all the power required to run the microgrid equipment and controls. And then last, the monitoring system also shows the power output from the battery and the battery state of charge. In this case, the system is not pulling any power from the battery. Now we're going to talk about applications of microgrids in North Carolina, and there are several. We are fortunate to have Tom Fenimore talking with us today about Duke Energy's experience, and he will cover these three projects in more detail. North Carolina Electric Membership Corporation, or NCEMC, is exploring microgrids to learn about integration of microgrid technologies. Currently, they have 2 pilot projects in operation that they are using to understand how they can apply the technologies to best serve their customers in the future. NCEMC and Tideland EMC partnered to install a microgrid on Ocracoke Island. NCEMC owns the supply equipment, including a 3-megawatt diesel generator, a 15-kilowatt solar array, and 10 Tesla Powerwall batteries rated at 500 kilowatts and 1 megawatt hour. A key feature of this microgrid is the inclusion of demand management technologies, which are owned by Tideland EMC. Both smart thermostats and water heater controls are deployed at customer sites and can be managed by the utility for demand response and load shedding. This area was in the news recently because of a major problem with the traditional grid. This microgrid did help keep the lights on for some loads. However, it was not designed to be able to carry the load for the whole island during tourist season. A second pilot project for NCEMC is located at Butler Farm. It will be an example of a microgrid located on the consumer side and is a multi-phase project. The hog lagoon at this farm has been covered to capture biogas that can be used in a dedicated generator. The project also has a conventional generator and a 20 kilowatt solar array. A Samsung battery will be added soon. The eventual plan for this microgrid is to power the distribution for 100 homes in the area. Duke Energy recognized that successfully designing microgrids for the future requires collaboration, and as a result, they created a group called the Coalition of the Willing as part of their Mount Holly project. When the initiative first started, there were only 6 companies, and over time it grew to 25 companies. This group of vendors worked on standardizing how grid technologies can integrate in the field. A key word for this initiative was interoperability, which they defined as make the various technologies on the electric grid work better together, more efficient, and at a lower cost. The focus was to develop a non-proprietary communications protocol so that devices can all talk to each other in the same language. This effort resulted in what is trademarked as Open Field Message Bus, a framework that is used to allow interoperable systems. We are now going to transition out of the technology focus and talk about policies and economic factors that may affect microgrid deployment. The concept of microgrids introduces questions about rate structures and pricing, ownership models, and standards and regulation. Rate structures and price signals from the utility are important to the economics and operation of microgrids. Examples of 2 types of rate structures that incentivize using electricity during off-peak hours in the summer are shown in this graph. Each line shows the change in the price per kilowatt hour anywhere from approximately 3 cents to 38 cents throughout the day. These types of rates more accurately reflect the changing costs of providing electricity by the utility throughout the day. The summer peak in North Carolina is typically between 3 and 6 p.m., and each of these rates reflect the higher cost of electricity at those times. The critical peak rate focuses on just the hours of 3 to 6 p.m. Higher peak rates, such as a critical peak shown here, could incentivize using microgrid applications for peak shifting and affect the economic investment. However, not every utility has these types of rates available. There are numerous approaches for ownership and business models, which can also present policy challenges. The business models involve different parties for the ownership, financing, maintenance, and operations of the microgrid equipment. There is the opportunity for microgrids to be installed by third parties, including technology providers or utility end-use customers. Or the microgrid can be solely owned by the utility. There are also hybrid ownership models called unbundled, where some key equipment is owned by a third party and other equipment or operation is owned or managed by the utility or customer. The different models result in either the customer having more control or the utility having more control, or somewhere in the middle. There's a good discussion on the different approaches to ownership in the SEPA and EPRI report that is referenced on this slide. There are some existing technical standards that address issues for microgrids, but there are also several under development. The Institute for Electrical and Electronics Engineers, IEEE, has developed 3 existing standards that address distributed energy resources, islanding, and energy storage systems. There are 2 IEEE standards under development that specifically address microgrids. One is for the specifications for controllers, and the other is for testing microgrid controllers. In North Carolina, House Bill 589 included a provision to conduct a study on energy storage technology. This study will address the potential for energy storage technologies to provide value to North Carolina consumers and address feasibility, economic potential, and recommended policy changes for the state. The results are targeted for December 1st, 2018. Another significant development in North Carolina was the approval of the Duke Energy project at Mount Sterling in Great Smoky Mountains National Park. This project was reviewed and approved by the Utilities Commission as an alternative to traditional transmission lines in April 2017. And several other states have introduced or passed legislation that specifically addresses microgrids and energy storage. In Maine, there was a concept draft bill that would establish rules to allow municipalities to work together with electric utilities to create microgrids. New Jersey approved a plan initiating the construction of microgrids at 13 sites to power essential services. And then New York has created a grant program to provide incentives up to $150,000 per applicant to promote microgrids in the state. Let's take a look at a few economic factors that affect microgrid deployment. First, we will talk about consideration for evaluating the capital investment. Then we'll cover potential for both economic and workforce development in North Carolina. The cost to install microgrids can still be quite expensive, but costs of some technologies, such as solar and batteries, have significantly declined in the last few years. To offset the investment, there are factors that affect the financial benefits. One factor is the electric rates and whether the microgrid will be used in demand response. Demand rates vary considerably across the country, and in the Southeast, they are still fairly low. Another factor is what the microgrid installation is being compared to. Is backup generation required already? When compared to installing standalone generators, there can be economic benefit. For example, one study by Nobles showed that for military applications, diesel microgrids compared to standalone diesel generators were able to be installed at a cost savings of $25 to $50 per kilowatt, or 30 to 60% savings. Most of the savings came from operation and maintenance of the generators. And then a big challenge to evaluating the capital cost is determining the value stream for certain benefits, such as resiliency. What is the value of keeping power when there is an adverse event? Some industries know this number, but it may be difficult to ascertain for a county or municipal facility that is providing emergency services. North Carolina has a strong energy sector, and microgrid industry growth presents an economic development opportunity. Many of the companies that participated in the Duke Energy Coalition of the Willing have a strong North Carolina presence. These companies manufacture various pieces of equipment in the supply chain used for microgrids. According to the Economic Development Partnership of North Carolina, we already are number 2 in the country as a smart grid cluster, with over 60 companies in the Research Triangle alone. The design, operation, and troubleshooting of microgrids is going to require a workforce that's ready to perform these duties. We are also fortunate to have multiple higher education facilities that have a focus on innovation in the utility sector, with the EPIC Center at UNC Charlotte and the Freedom Center at NC State University. There are also several community colleges with programs that focus on training for the utility industry. These programs, again, set up North Carolina to be a leader for microgrid development. There are numerous challenges and risks with integrating microgrids into the grid, and we are only going to cover a few. There are both technical challenges and policy challenges. Many utilities are exploring pilot projects to address technical challenges, and regulatory bodies are looking at changes in policy that may be needed. Interoperability in communications is a key technical challenge with all the different pieces of equipment, generation, inverters, switches, and battery control. This is a key area that both standards and demonstration projects will continue to address. One specific part of interoperability is unscheduled islanding and the island-to-grid transition. Currently, controllers must be customized for each application. And while battery technology has progressed, it's still considered expensive in some areas. One of the frequent overlooked aspects of battery systems is the cooling needs. The cooling needs of a battery system can contribute a significant amount to the auxiliary power requirements. Other components, such as controllers, also require some power. Other challenges that were mentioned earlier include how to regulate microgrid development and their operation, especially with the multiple business models. As stated earlier, the business models involve different parties for the ownership, financing, maintenance, and operations of the microgrid equipment. The traditional utility business and regulatory model of centralized generation is challenged by microgrids, especially when there is the potential for third-party ownership and operation. There are, of course, numerous benefits to installing a microgrid, which generally fall into the category of resiliency, sustainability, and economic growth. One primary advantage with the microgrid is outage protection. Some customers require this, such as hospitals, emergency service centers, and military bases. Other customers would benefit during adverse events to power certain critical loads, such as refrigeration. The addition of storage that comes with microgrids allows renewable energy integration that could be shifted to also help with peak reduction. North Carolina is a top developer of utility-scale solar. While the solar helps with overall energy needs, it does not always produce power at the peak times of day or year. Similarly, the storage system could be used for load management, or non-critical loads could be curtailed as part of a demand response program. And of course, there are economic development benefits. With so many technology companies located in North Carolina, continuing to embrace modernizing our approach to grid design will help bring in more money to our state. And at this point, I'm going to turn it over to Tom Fenimore with Duke Energy to tell the story of how Duke got started with microgrids, what they have learned in particular from McAlpine, Mount Holly, and other projects, and where their business is going. Tom?
Thank you, Cece. Good afternoon, everyone. It's a pleasure to spend some time with you this afternoon and talk about microgrid efforts at Duke Energy. Duke Energy is heavily involved in testing and deployment of microgrid technologies, and we're going to take a look at current projects at Duke Energy and also some of the projects that are going on in the R&D area at Duke Energy. Starting with the regulated projects, we have a number of regulated projects that have been ongoing for a few years, and they expand all across our territory now, and we're currently engaged in conversations with our stakeholders at the regulatory level in basically all of our jurisdictions now. So the microgrid efforts have expanded beyond North Carolina and extend throughout our territory now into not only the Carolinas, but also Florida, Ohio, Indiana, and Kentucky. Our current deployments on our regulated business side include a mix of both research and development as well as technology pilots to understand the capabilities of microgrids. In North Carolina, we have the operational microgrids at the City of Charlotte Fire Station 24, which was Duke Energy's first technology pilot to understand what it actually took to build out and operate a microgrid to support a customer, to understand resiliency, reliability, and all of the issues around microgrid operations for a customer. Our Mount Holly Training Center is our microgrid innovation lab, which allows us to test advanced technologies in an environment where no customers are affected. That essentially is a lab environment where we have our own loads that we work with so that we can understand the operation of equipment and test it in a way that will not affect any customers. Do that in a way that allows us to understand those technologies before we scale them. An exciting project that was recently made operational is our Mount Sterling project. At the National Park radio service towers in the Great Smoky Mountains National Park, a DC microgrid was deployed to support those radio communication towers for a period of up to 7 days of no sunshine. And that allows those towers to operate at the most critical time that the National Park Service will need them. In Florida, we have operational the University of South Florida St. Petersburg campus. There is a multi-use parking structure which contains both battery and solar to operate that parking structure, along with some other facilities attached to that parking structure should we have an outage at that site. And in the business development side at Duke Energy, we currently have business development ongoing at military bases throughout our territory, folks like the City of Charlotte who are investigating the opportunity to deploy a microgrid at their command and control center for emergency operations at the city. And then also facilities like the Convention Center in Anderson, South Carolina, which is an emergency response center for the city of Anderson. And we all know with the number of weather events that we've had lately that facilities where you can host a large number of people and actually operate as an emergency center are critical to the operation of facilities. On the commercial side of Duke Energy, which is the unregulated arm of Duke Energy, so to speak, we have projects that are in operation at the Schneider Boston 1 campus. This is Schneider's corporate headquarters in the U.S. And we also are engaged with Montgomery County, Maryland, 2 projects under construction that will be completed and made operational in early 2018. Speaking about McAlpine directly, however, this project was undertaken in 2013 to understand exactly what it took to operate a microgrid on the distribution network and provide backup power to a critical facility at the City of Charlotte. The project actually worked out to be kind of a perfect storm in that the City of Charlotte fire station was actually located physically right next to the substation where the solar and the battery were already deployed. Looking at this schematic, you can see that we have a battery, a 200 kW battery and a 50 kW solar field that are connected together to feed the fire station through their existing service so that the customer does not have to make any changes to their wiring. So we went into the project with a number of goals and objectives that we wanted to achieve, the first of them being able to provide resiliency to a critical facility and actually own and operate the assets on the Duke Energy side of the meter. The intention is to not make any changes behind the customer meter. And in the utility world, to do things at scale, it's necessary that you have standardization. So our intention was to use off-the-shelf components, things that we have in our storehouse, reclosers, switches, controls, etc., to build a microgrid and to operate it and get satisfactory results from that. In addition to actually providing backup energy to the fire station, we also wanted to demonstrate ancillary and grid services. What are the values of microgrids when they're not actually backing up the customer? In this case, providing frequency regulation, things like solar smoothing, potentially demand response if needed, and volt bar support for the grid. All of those have been tested at McAlpine and made operational as part of the microgrid. And last but not least, from an objective and goal standpoint, was to gain operational experience. Energy storage is a relatively new technology coming into the grid, and we wanted to have some hands-on experience and then what it actually took to operate these energy storage devices. Thermal management was an area where we needed to gain some understanding. What did it take to actually have to air condition a battery, and how did that respond in the hot, humid summers that we have here in North Carolina? And then last but not least was understanding the O&M challenges. What are the things that we need to understand about operating a microgrid that are different than the other grid technologies that we have out there today deployed throughout the Duke Energy territory? The project went operational in July of 2015, and we had multiple weather-induced events of the microgrid, which caused it to operate and automatically disconnect from the grid and reconnect back to the grid. And the last of those events was actually last Monday night, as the remnants of Hurricane Irma came through Charlotte. We had some wind-induced events that caused the voltage to drop on circuit 2414 at that substation. And doing what it's supposed to do, we disconnected from the grid, ran the fire station on battery, the energy storage system providing all the power that the fire station needed for a period of time. And then when the weather calmed down and the circuit voltage became normal again and stabilized, we reconnected and resynchronized back to the grid. Some of the findings that we've had regarding microgrids has been an eye-opener in that we've had some inverter capacitor failures that we didn't anticipate. As has been referred to in this webinar previously by Cece, we've also had some thermal issues in the battery container. Air conditioning batteries on a continuous basis is a challenge, and it's really necessary that a good thermal understanding of what is involved in the cooling of them takes place on the front side, and the right engineering folks are sitting at the table. Some of the things around battery charging and string imbalance became evident when you have a large number of batteries all connected in series and parallel. Keeping them charged and balanced is quite a feat. And systems actually do overall a very good job of that, but we did find that we had some imbalance problems popping up from time to time. The other thing that we found out was that we had large standby losses. Batteries sitting there idle for a long period of time can have standby losses that pop up, and this can contribute to the overall energy use of the microgrid when it's idle. However, we also found out that this microgrid has become an outstanding educational tool. We hold multiple tools and demonstrations per month. We engage our internal and external stakeholders by showing them the components that make up the microgrid, and then we also use it as an educational tool for our local colleges and universities in their power engineering programs. Looking at the overall site of the McAlpine microgrid, we have a 50 kW solar field in the front of the substation. The energy storage system, the battery, is contained to the upper right-hand corner, and the fire station, as I said, is ideally located across the fence at the substation, allowing us to serve the customer through their existing service feed from circuit 2414. The actual islanding event process that takes place when we do disconnect from the microgrid and support the fire station looks like this. This is the actual first event that we had at the fire station on April 30th of 2016. At 8:20 p.m., the battery was charging on a Saturday evening, and at the battery was charging at 100 kW. The fire station load was 10 kW. The auxiliary power was 4 kW. So we were importing from the grid 114 kW total. A thunderstorm rolled into the South Charlotte area around 8:24 at that same time, and we had a voltage disturbance at 8:29 p.m., which caused the island switch to open. The battery automatically switched from charging to discharging to supply the power to the fire station and also to the auxiliary loads. And within 2 minutes, the circuit restabilized, and at 8:30 p.m., the island switch resynchronized back to the grid and reconnected back to the grid. The battery went back to an idle condition and was ready to operate again if it needed to support the fire station for microgrid operation. This was our first unattended islanding event, and everything operated as planned. And we've since had several other events where the operation has been exactly the same way. Moving on from McAlpine, we realized that if we connected customers to our microgrids for research projects, that we were going to limit ourselves in the amount of testing that we could do. And we saw an opportunity to use the space that we had available to us at our Mount Holly site, which was an old training center. That site has been developed into our Microgrid Innovation Lab. And you can see from this picture, we have 110 kW of solar up in the upper right-hand corner, a 650 kW energy storage system. We have the shop area, which is the load for the microgrid. a 10 kW solar field on an overhead structure for a parking area, and our microgrid switch yard, which enables us to change out technologies and integrate them into the microgrid for testing purposes relatively quickly. One of the things, as I said, at the Microgrid Innovation Lab that we were striving for was the ability to continue to develop our microgrid control experience and do that in a way that if we made mistakes, we wouldn't affect customers. This allowed us to move into the area of testing some advanced inverter technology, to understand the different modes of operation of these inverters, and how to actually get on and off the grid in this function called seamless islanding in more ways than we were deploying it just at McAlpine. We were also able to integrate multiple distributed energy resource systems to understand droop mode operation, which essentially is the way to operate multiple generation devices in a power distribution system. And this project will actually be expanded to the entire circuit, Circuit 1208, and an optimization scheme is being developed to understand how to operate all of these devices together in a harmonious nature, because the future at in our energy systems is that we will have multiple sources of generation, solar, battery, customer generation. They're going to have to operate together. And as a utility, we need to understand how to operate these devices in the best way, not only for our customers, but also for the grid and the health of the grid. As Cece had mentioned, a project that was undertaken out at the Mount Holly site was the field message bus architecture development. That development continues to go on today, and we continue to move things forward by testing out the various pieces of that architecture and developing that with the standards body so that that can be published to the utility industry and taken advantage of. We continue to gain operational experience with batteries, and we continue to operate the microgrid that we have at Mount Holly. It is our second generation microgrid. We have baselined the operations with the existing controls that we have there, and as we move towards the field message bus architecture, we will have a comparison so that we can actually compare the operation of standard traditional controls versus field message bus architecture mode operation. Once again, we have another outstanding educational tool that we can take advantage of for tools and engaging our stakeholders and teaching our power engineering students at our colleges and universities about microgrid operation. Looking at this particular operation screen, this is the one from Mount Holly, we see that we have multiple devices, many more than we had at McAlpine, all operating harmoniously for the most part. It is a test environment. And this is the place where we can develop these technologies and understand how they operate together or may not operate together if we find operating schemes where the different devices don't act well together. It's important that we do this in a lab environment. The Mount Sterling microgrid was our first regulated microgrid deployment. It was made operational in the summer of 2017. As we talked about earlier, this is at the top of the Mount Sterling Mountain in the Great Smoky Mountains National Park, where the emergency communication towers are located. This particular site was served by the 12,000 volt Waterville Village feeder, which is a 4-mile line running up through some very unhospitable territory on the side of a mountain feeding that customer load. The intention was to provide power to that site on a continuous basis, and because it was an emergency communication tower, the operation of the system was critical during periods of inclement weather, and that is exactly when we had the outages of the traditional utility line running up the side of the mountain. With the deployment of the solar field to charge the batteries and the battery supplying the load to the communication towers, we now have the ability to provide uninterrupted power to the communication towers at the Great Smoky Mountain National Park and ensuring that they're online at the times that they're needed most. So this was our first regulated rate-based project. The beauty of it is that we were able to increase the reliability of the communication towers during inclement weather, which is exactly what microgrids are designed for. We actually were able to decrease our O&M costs to our rate-based customers. We're going to eliminate 4 miles of high-maintenance 12 kV line. Maintaining that line was a difficult thing that often required helicopter operations to get folks up and down the mountain to repair that line. we were able to integrate the green technologies into the microgrid and actually return 13 acres of right-of-way back to the national park. We've been in operation since May of this year. We're currently undergoing performance testing, and we will actually remove the existing 12 kV line in 2018. Currently, it serves as a backup for the microgrid so that we have a backup just in case the current technology that we're putting in line does not meet performance testing, but all indications are that it's operating extremely well. Once again, during Irma, we had uninterrupted operation of the microgrid and the communication towers in western North Carolina, and we were actually taking outages in the western part of both North and South Carolina during the storm last week, so it was really good to know that. Our commercial Duke Energy business, which operates outside of our regulated territories, as I said, is engaged in development of some microgrid projects with Schneider, and the one that's in operation currently is at the Schneider Boston 1 campus headquarters. That's the U.S. headquarters for Schneider, and that particular project was developed jointly by Schneider and Duke Energy and is being used to do testing and development, as well as provide backup energy to their headquarters in case of a grid outage. Duke Energy Renewables, the commercial arm of Duke, will own and operate the system and will sell power to Schneider that is generated from the solar field under a power purchase agreement. And Duke will continue to operate that system and at a future point integrate energy storage into the system for additional microgrid operation and ability. So that's an overview of the current efforts at Duke Energy, and at this point I'd like to turn it back over to Alex.
Great. Tom, thank you so much. We appreciate those examples and the explanations that you provided. You and CC both covered a lot of ground and definitely helped us gain a better understanding of microgrids and grid resiliency, as well as the challenges and the opportunities of integrating microgrids into our electric grid. Folks, I hope that this webinar has given you a helpful overview of the technology and how utilities are using it to improve their operations and their services to customers. Now, before we get into the Q&A period, we'd like to remind everyone that we will continue with the last webinar on self-optimizing systems next month on October 24th. So please mark your calendars. And we're excited to take a deeper look at the self-optimizing technologies. So we hope that you'll join us again, and please keep a lookout for an email invitation with that registration information. Also, as a reminder, you can find all of our resources, the case studies, educational videos, and other links at our website, ncsmartgrid.org. You'll also find links to the resources that were referenced in today's webinar, including the SEPA and EPRI report that CC mentioned on expanding applications, implementations, and business structures of microgrids. You'll find the 50 States of Grid Modernization quarterly report, which is published by the NC Clean Technology Center. That report provides policy and regulatory information from different states. And also, you'll see a link to the Microgrids group at Berkeley Labs that studies consumer adoption patterns of the microgrid technologies as well as microgrid controllers. So please visit our website, ncsmartgrid.org, for access to all of that information. At this point, we'd like to open it up and take a few minutes to answer some of the questions and comments that have come in during the webinar. Please understand we may not have time to answer all the questions, or we may not have an immediate answer to some of the questions that have come in. In either case, we will do our best to follow up with you after doing some research or finding the best resource for you. Cece, let's take a look at some of the questions that have come in.
Thanks, Alex. Yeah, we have a few questions that have come in. The first question that I see here is, do consumers need to be concerned about safety with microgrids? And I'll take this one. All electricity and energy comes with safety concerns, and safety is the #1 goal for utilities. So the standards that are being developed are important to lay the groundwork for a safe grid. And safety is part of why utilities are installing these pilot projects so they can understand any technical challenges and get their staff trained. And then all the equipment such as sensors, switches, and disconnects are part of the safety measures. And another question that we've got is, can you tie electric vehicles into a microgrid? And I'm going to turn that one over to Tom.
Okay. Thanks, Cece. The short answer is yes. We have some projects where we're looking at integrating electric vehicles into microgrids. This adds another layer of controls and ability and energy sources into the microgrid. And electric vehicles make a nice system to be able to do that with, because they're capable of both charging and discharging, and can be stationary for a period of time to where they could actually become a resource for a microgrid.
Okay, great, thanks. And we're going to do one more question in the interest of time. So another question that we've gotten in is, what have you found to be the biggest challenges in operating microgrids? So again, I'm going to turn that one over to you, Tom.
Yeah, thanks. Yeah, some of the lessons that we've learned from our experiences at McAlpine and Mount Holly have shown that the overall technologies, the solar and the battery energy storage systems, they operate as they're intended. One of the things that we have determined, however, is that cooling systems for the batteries need some attention in the fact that there's some work that needs to be undertaken as these systems are developed to truly understand the application and the heating and cooling systems that need to be designed for the batteries. That, along with the IT networks and communication systems, can be problematic if not well understood and planned for. So we've found that during transitions from on-grid to off-grid, the islanding event, that if IT networks and communication systems are not kept operational during that transition, that can create some problems for the control system. So some findings that we're engineering into our systems as we go forward. And so that's a great question, however, because that is our intention with operating McAlpine and Mount Holly, is to find those things before we do microgrids at scale.
Great, thanks, Tom. So those are all the questions that we can answer at this time, and if we didn't get to your question, we'll reply directly to you within the next couple days, and I'm going to turn it back to Alex.
All right, Cece and Tom, thanks for taking a few minutes to answer those questions that came in. At this time, we're going to wrap up with our video from Duke Energy about microgrid technologies. And before we do, what we'd like to mention is that the video is going to be on Duke Energy showcasing a system in Charlotte, North Carolina that is supporting a critical services facility. So we saved this video until the end because depending on your internet connection, you may experience some lag time or minimal delays in viewing. If you have any problems watching the video, give it some time. It should play for you, no problem. But also, please check your inbox for an email from us after the webinar ends that will include a link to this video so that you can watch the video at your convenience and have a link to it. Also, we will include our satisfaction survey in that email, and it would help us a lot, and it also helps us improve if you'll fill out that survey so that we can continue to make these webinars valuable for you. Folks, we're grateful that you chose to take time out of your day to join us for the webinar. We hope that you enjoy the video and have a great rest of your day. Thank you so much.
A microgrid is a number of pieces of equipment that are combined together to provide seamless power to a customer in the case of an emergency or the case of a severe weather event. The geographic location here was perfect. The customer was located on the other side of the fence, literally from the substation, and that worked out extremely well for us. We recently had an event, a thunderstorm rolled through the South Charlotte area. The microgrid operated automatically that evening. When it saw the voltage on the circuit drop, it disconnected from the grid, supported the customer for several minutes, and then when the electrical storm passed and the circuit stabilized again, it automatically reconnected back to the grid completely seamlessly and automatically as it was designed. Part of the microgrid operation is a control house that basically is the nerve center for operating the microgrid. The job of the control house is to house the electronics equipment needed to make decisions when we're operating as a microgrid or when we're operating grid connected. This is a containerized energy storage system that contains 500 kilowatt hours of electricity, roughly a day and a half's worth of electricity to support the fire station in a typical operating mode. On June 17th of this year, we had an opportunity to disconnect from the grid and support the fire station for 26 hours, which gave us a really high level of confidence that should we have an emergency situation, we can expect to be able to support the fire station for an extended period of time. The McAlpine microgrid concept is one that we're actively working with customers on now to develop offers around. We're currently engaged with the Department of Defense at Camp Lejeune, at Cherry Point, to understand how we can offer this to them as a service going forward. McAlpine microgrid was a milestone not only for Duke Energy but also for the electric utility industry, because we successfully combined solar and battery to provide a seamless disconnection from the grid and reconnection back to the grid of distributed energy resources that provide 100% reliable power for a customer.